Hi, this is Tzvi Rosen. Today I'm going to be picking up with the second week of online lectures for MAS 4301 Modern Algebra. I'm going to be talking about some more examples of groups and some properties of groups. Okay, the first example of a group that we'll look at is the dihedral group d sub 2 times 4. There's, depending which source you look at, people call this d sub 4 or d sub 8, and in general people call it d sub n or d sub 2n. I think this is good because then you know exactly. The reason that people use both of these notations is because the group has 8 elements, but it's the group of symmetries of a fourgon, i.e. a square, a regular fourgon. So I'm just going to keep it as d2n so that it's as unambiguous as possible. Okay, well the idea here is we take a square and then we consider the maps from R2 to it. So this is a square sitting in R2, and we want to consider the maps from R2 to itself that preserve this square. Okay? So, and we're talking specifically about rigid motions, rigid maps. So we're just moving things around without otherwise changing anything. So one thing that we can do is we can rotate the square. Okay? If we do that, then each vertex goes to its neighbor. We're going to call this element of the group F. Then another thing we could do is reflect across this line of symmetry, sending this vertex, so the vertex 1 to vertex 2, and vertex, we usually call this 3, this 4. This will be 4, this will be 3. And vertex 3 and vertex 4 will swap places, and that we'll call G. Okay? So this is these are maps, and so in a certain you can think about it as a subgroup of the group of mappings of R2 to itself. So d2n equals, this group will be considered, and I'll still call it d of 2 times 4, be equal to maps preserving the square these are also called symmetries of the square. And the operation on these maps will be, the binary operation will be composition. So it will be denoted by a little circle between maps. So let's think about what happens with this with these operations as we apply them. So I want to consider how F acts on composition with itself and with G. So if we do F once, that's rotation by 90 degrees, 90 degrees counterclockwise. F squared, well, if you rotate it 90 degrees and then another 90 degrees, this you can also denote it as F composed with F, this is a rotation by 180 degrees. If we do F 3 times, that will be rotation of 270 degrees. Hopefully this is obvious at this point. And if you do F 4 times, then you come back to the identity, which we'll denote by E. What happens with G? So if we do G, this is flipping or reflecting over the line y equals 0, or x equals 0, I should say. And if you do G squared, well, if you reflect twice, you come back to where you started, so that's equal to E. Okay, so if that covers powers of F and G, let's just remind ourselves that this is G composed with G. How about F composed with G? So if we do F after we do G, okay, how does that act? Well, we're rotating it once, so everything here, let me make a copy of this so that it's easier to see. Make it a bit smaller. Okay. So after we do the first rotation, sorry, the G is first. So first we swap 1 and 2 and 3 and 4. So our new markings here should be 1 and 2, and this will be 4 and 3. Okay, so it's kind of changed the numbering, so it's no longer going around counterclockwise, it's going around clockwise. And then if we do F after that, and remember, whenever we're composing maps, the rightmost is the one we do first, and then you move towards the leftmost. So this is after F, after G, I'm sorry, after G, and now after F, what we'll get, so we want to rotate everything counterclockwise once. So after rotating counterclockwise 90 degrees, we'll get 1, 4, 3, 2. Okay? Now let's consider how else we could have gotten to this orientation. What if we, before we flipped, we rotated? Okay, so let's say we rotated once, or let's say we rotated once in the clockwise direction, so that's 3 times in the counterclockwise direction. So let me make things a bit smaller to fit on the slide. Okay, so if we were to do f cubed first, that would give us instead of having 1, 2, 3, 4 going around that way, we would have 1 starting in the bottom right corner, so we would have 1 here, 2 here, 3 here, and 4 here. And then, after getting the 1 in the bottom right corner, if we flip along the line x equals 0, if we reflect across that line, what we'll get is the same thing we have over here in the second picture. We'll get this. So summarize, so this is after G, this is after F, this is after F cubed, and this is after G. So, to summarize, we have that Fg equals G F cubed. Okay? So this is an example of a non-abelian group. Right? Because if it were abelian, you should have Fg equals Gf, but no, it's Fg equals Gf cubed. And we'll see more general relations on dihedral groups. Okay, if we have, instead of a fourgon, a square, a regular fourgon, in our case a square, if we have instead a regular n-gon, I don't know how much I should make n to make this look reasonable. Let's make it 7. Once things get past 7 or 8, it's hard to remember that that it's not just a circle. Okay, this is certainly not regular, but hopefully it's close enough. Now here we're going to have similarly one map which is rotation by 90 degrees. So that will be F, which will be 90 degree rotation, sorry, not 90 degrees, 2 pi over n radians, 2 pi over n radians counterclockwise. And then you'll also be able to take not the same line as we had before, but a different line of symmetry. So let's say something like this line. Okay, so it'll pass through this vertex, then the midpoint between these two vertices. And you'll be able to swap the vertices on the corresponding sides of that line of reflection. And that'll be our G. And this will generate all of the different symmetries of the n-gon. I say that it generates because you might need to multiply. There are maps where you need to multiply these two together in different ways to get all of the symmetries that you're looking for. But if you take them all, this will guarantee that that you get all the symmetries. So we should check briefly whether the group axioms are satisfied. So remember we have 4 group axioms: closure, associativity, identity, and inverses. Okay. Well, if you have 2 maps that preserve an n-gon, then when you compose them, they'll also preserve an n-gon, so that works. Associativity you get from the usual associativity of composition of maps. Identity, just map it to itself. Inverses, whatever you did, undo it. So if you rotate clockwise, if you rotated counterclockwise, go clockwise. If you reflected, reflect again. So this checks all of the group axioms, and we're going to learn a lot more about this group subsequently. Okay. So this is an interesting theoretical example. So let's say you have S, an infinite set, and I claim the following, that this modified A of S. So remember that A of S equals the set of all mappings from S to S. So we're going to define A of S tilde to be equal to the set of mappings from S to S such that let's give it let's name it something, F from S to S, such that F of X equals X, i.e. it acts as the identity for all but finitely many X in S. Okay. So this is tricky because now we're dealing with infinity and finite sets and complements of finite sets. So we have to be extra careful here to check the axioms. So if we have, no, I don't like that color. If we have two maps with this property, so let's say we have F composed with G. So let's consider the set of indices, the set of elements of S where G is not the identity. Okay, and this should be bijections, of course. And here as well. So if we have the closure F composed with G, so we can consider the subset of indices where, subset of elements of X where G is not the identity. So that's T in S, where T is a finite set. And then we can consider separately, let's call this T1 actually. Consider, so this is equal to the set of X such that G of X is not equal to X. Okay? And similarly, T2 is another finite set defined as the set of X. Let's use set builder notation, why not? X such that F of X is not equal to X. Okay. Well then, F composed with G, so when you do G and then you do F, this is the identity except at most on T1 union T2, right? It might be the identity inside of there also, but T1 union T2, we know since both of them are the identity everywhere outside of that union, their composition will also be the identity there. T1 union T2, but the great thing about two finite sets is their union is also finite. So that means that this composition is also within our A of S tilde. Okay, and what else do we have to check? We have to check associativity. This is something we inherit from general A of S. Okay, inherited. We need an identity. That's just the identity map, which is the identity map on all indices. So certainly it's not the set on which it does not act as the identity is finite. Okay, so this is in A of S tilde. As for inverses, you just have to check that if the map, if a certain map F has an inverse in A of S, if it acts as the identity on all but finitely many sets, then so too the inverse does. And that's obviously the case. So if F is in A of S tilde, then F of X equals X for all but finitely many X. And that means that f inverse of x is also the identity on all but finitely many. X and S. Okay, so that proves that this is a group, even though we defined it using kind of more abstract concepts than some of the other groups we've described. It certainly satisfies all of our axioms. Okay, let's think about some things that aren't groups. So if we were to consider just the set of integers, okay, so this is -2, -1, 0, 1, 2, and you're going off in each direction. And I wanted to use multiplication as a group operation. Well, this is a well-defined operation, obviously. You can always multiply two integers, and closure works, right? So let's use this for axioms. Closure. If a and b are integers, then ab is an integer. Right? That's great. Associativity also works. Just by definition of the way we multiply things. Identity, we do have an identity. 1 multiplied by anything, 1 times a is equal to a times 1 is equal to a. So that's good. But inverses is where we get tripped up. Inverses, the only numbers that have inverses are 1 and -1. So that gets a big fail. And in the first class we mentioned that this is an example of something called a monoid. Is it a monoid? It might be a semigroup. I'm going to hold off on that until I check later. Okay. So now let's consider another non-example of a group. If we have points in the plane, we want to send a given point to points in the plane. This should just be R. Elements of R, and then a binary operation on elements of R, taking two real numbers and mapping it to the square of the first times the second. So I want to check this out. So if a and b are in R, so in terms of closure, if a and b are in R, then I need to write down the words that I'm saying. Closure. If a and b are in R, then that means a squared b is also in R, so that's good. Associativity, here we run into trouble. So let's say we're trying to do a, and if our operation is star, b star c equals a star b star c, well then this is equal to b squared c, and then a starred with that. This is equal to a squared b, and star with c, and then we have a squared b squared c. Let's leave some question marks here to make sure we don't know. And this is the square of that first term, so a to the fourth b squared times c. So obviously these are not equal. So our non-group here fails the associativity axiom. And then checking the other axioms would lead to all sorts of frustration. Okay, here's another one, another non-example of a group. If we have the natural numbers 1, 2, 3, 4, etc., and we're using addition as our operation, then certainly closed, right? Because if you have two natural numbers, a, b, and n, then a plus b is also an n. If you have, so the next is associativity, and addition is associative. A plus b plus c equals a plus b plus c, and you can think about how adding two natural numbers is like taking two groups of that size, putting them all together, and then counting it again. So it doesn't matter if you put two groups together and then pull in another group, or you mix that group with that group first and put the other group with them, you would still end up with the same set of objects. So this is certainly fine. In terms of identity, here's where it fails, because we don't have the identity. We're not including 0 in this understanding of the natural numbers, so 0 is not here. So it fails the identity axiom. It also fails, for that matter, the inverses. Okay. So I wanted to explore a little bit what we could do to find all of the groups that we can for small sizes. Okay, so we know the group axioms at this point, and now we're just trying to understand what kind of structure those axioms impose on sets of a small size. Okay, and the way we're going to do this is using what's called a Cayley table or a multiplication table. And the way that this works is you take all of the elements of the group and then in each of the spots you indicate which element of the group is given by the binary operation A star A, which is given by the binary option A star B, etc. And then here you have B star A, C star A, etc. Sorry, this should be B star B. This would be B star A. Okay, and you notice that these won't necessarily be the same unless the group is abelian. So if your group is abelian, it'll reflect really nicely along the diagonal. But if it's not abelian, you'll get all sorts of different things in this matrix. You can have all sorts of asymmetries. Just as a quick check, let's do the group of Z mod 3Z. Let's do the Cayley table for Z mod 3Z. To make sure we have the hang of it. So we're going to put E here, that's 0. Then we'll have 1 and 2. Okay, and we're doing addition, obviously. This is a group we discussed in class. So when I take 1 plus 1, I get 2. So I put that here. When I take 1 plus 2, I get 3, but 3 mod 3z is 0, so we get our identity element. Similarly, when we take 2 plus 1, same deal, because this is an abelian group, and 2 plus 2 gives us 1. Okay? So that's how we use a Cayley table with a group that we understand pretty well to list the results for each of our binary operations. Okay, so now let's consider, without any foreknowledge of what the group is, let's consider what happens if we look for a group of size 1. Well, if the group has size 1, so if the group has size 1, we know that every group has to have an identity element, and that's all that it can be. Okay? So we just have the identity element. It's its own inverse, so it satisfies the inverses. When you compose it with itself, it gives itself back, so it's closed, and certainly it's associative. So this is our first group, and its Cayley table is just itself. Okay. How about n equals 2? So we're looking for groups of size 2, so we're going to have two elements, E and A. Okay? So what will our Cayley table look like? Okay, so we have, obviously, E times A is A, and A times E is A. What is A times A? Well, because there are only two elements of the group, if we have closure, A times A, it must be either equal to E or A. But what do we know about, what else do we know? We know that A has to have an inverse. Okay, so if A star A were equal to A, then A wouldn't have an inverse, because there would be nothing you could multiply to get E. So it must be A times A equals E. Okay? So the fact that we were able to deduce every element of the Cayley table tells us that there's only one group of this size. One group of size 2. Okay? And I'll just write a quick note here. This is because of inverses. Okay. What about groups of size n equals 3? Well, then we have G equals EAB. And let's draw a Cayley table. EAB, EAB. Okay. So there are two possibilities. We know that, well, let's see what let's think about what these possibilities are. We know that if we have elements of the group, every element in our group has to have an inverse. Okay, so E is its own inverse. So then either A and B are inverses to each other, or A and B are their own inverses. Okay? But that leaves us with a bit of a problem, because if we have A and B are their own inverses, then what is A times B equal to? So if it's E, then A and B are each other's inverses. Okay, so A, B are inverses. So that's fine, but that's not what we were supposing. So if it's A, well then, if A times B equals A, I can multiply on the left both sides by A, supposing right now that A and B are their own inverses. So then star A here, and then you'll also get AA on this side. This reduces to the identity because A would be its own inverse. So this would tell us that B is equal, and this also would be the identity. That would tell us that B is the identity, but that contradicts our supposition that B is one of the other elements of the group. So this tells us that this is impossible. If you do the same analysis, you'll see that this is also impossible. So you have to have that A times B is equal to E. And by the fact that inverses are two-sided, you know that B times A will also be equal to E. Okay, well then what's A squared and B squared equal to? Well, if A squared, so we know A squared can't be equal to A, because then you could cancel and find that A is equal to E. So instead, so that rules out A. And we know that A is not its own inverse because we already found its inverse. So that means that this must be B. And by the same token, this must be A. So here, all of our decisions here were forced just by the group axioms. And this gives us the unique group of size 3. And if you look back on the previous slide, you'll see that this looks pretty much identical to Z mod 3Z. So this is only one group of this size. and it's isomorphic to Z mod 3Z. Okay. We'll quickly pause here. Okay, picking up where we left off. Now we'd like to consider groups of size 4. Okay, so we'll do the same strategy. We know that there are 4 elements, so it'll be E, A, B, C. Now let's consider what the Cayley table looks like. So, because there are 3 non-identity elements, 2 of them can pair off to be each other's inverses, but then one of them has to be left to be its own inverse, right? So let's just call that one A. It'll be its own inverse. Okay, so that so far we're not making any assumptions about the group. Like, we're forced to have one of them be its own inverse. Okay, so now if B and C are inverses with each other, then that helps specify things. But it's not, they're not necessarily inverses of each other. So it could also have that B is its own inverse and C is its own inverse. Okay, so let's suppose for right now that, so let's say this will be case 1, where B squared equals E and C squared equals E. We're going to put an E here and an E here. Well then, if we have AB, so now we have to consider what AB and all of these other products are. So if AB, we know that AB has to be equal to E, A, B, or C. We know that since A is its own inverse, AB is not E, because inverses are unique. We know that AB can't be A or B, because then you could cancel, so that leaves only one option. So this will have to be C. The same reasoning will lead you to believe that this is B, and this is A, and this is C, B, and A, again by the same reasoning. And so what that tells us, first of all, is that this is an abelian group, and this is the one group of size 4 if you assume that A, B, and C are their own inverses. Okay, so that's case 1. Let's consider the next possible case. So NG is E, A, B, C. So we're going to draw a Cayley table, E, A, B, C, E, A, B, C. And here we're considering case 2, where BC equals E. So we know that A squared is E, and BC is E. Okay, since inverses are two-sided, CB is also E. Okay. Well, now we have to figure out what these other values are. So AB is going to be A, B, C, or E. We know that A squared is E, so it's not going to be E. We know that it can't be A or B, because we could cancel, and that would imply that A or B is equal to E. So that leaves AB equals C. Okay? And then if AB equals C, we can multiply on the left of both sides of this equation by A to get A squared B equals AC, or since A squared is E, that means B equals AC. So that tells us this is B. Okay, as for BA, how do we want to do this? So if we have BA, well, let's start with one of the multiplications that we know. we have AB equals, or rather AC equals B. If we multiply on both sides by C on the right, we get AC squared equals BC, which tells us that this is equal to E, so we have AC squared equals E, or multiplying by A on both sides, that tells me C squared equals A. Okay. By the same token, so I've got a lot of deductions here. By the same token, if we take B squared, so we know AB equals C, and that tells me that AB squared equals CB, which is just E, and that means that B squared equals A. Okay? And once we have that B squared equals A, we have B squared A equals E, and then multiplying C on the left, we get CB times BA equals C, and because CB is equal to E, this means BA equals C. So we have a C here. And it's not hard to deduce in a similar way that CA, well, let's just go ahead and do it. Because C squared equals A, where shall I put this? Okay. We can get C squared equals A and then multiply on the right, on the left by B. We want to multiply on the right by B, on the left by B. We want to get CA. So let's multiply C squared equals A on the right by A. Get C squared A equals A squared, which is E. And then multiply on the left by B. So BC squared A equals B, sorry. But then you know that BC is E, so this means CA equals B. So that tells us this is B. So this, all we did was deduce all of these entries after we specified that BC equals E. So what we can deduce from this is that there are exactly two groups of size 4, one of which has this multiplication table, and one of which has this multiplication table. Okay, and we'll go into those groups later. But you can see that already the group axioms give us a lot of structure and specify a lot of information that we wouldn't necessarily assume straight off. Okay, so now let's deduce a few group properties. So we want to show that the identity is unique. So that means that the E and G such that AE equals EA equals A for all A and G, this is unique. So that if there exists E and F and G such that both satisfy these properties, then E equals F. Okay? It's not hard to get this. In particular, you know that EF, because F is the identity, this has to be equal to E. Or rather, how would we describe this? But because E is the identity, it's also equal to F, right? So it's pretty straightforward, right? This is let me put it this way. Consider EF, because F is an identity, EF equals E, right? Because multiplying by F doesn't change E. Because E is an identity, EF equals F, because multiplying on the left by E doesn't change it. So that means that you have the same thing, EF here and EF here, equal to EF, E and F, so that means that E equals F by the transitive property of equality. Okay. A little QED square. Okay, now I want to prove that the inverse is unique. So same deal. Let's suppose that there's two. Okay, let A be an element of the group. Suppose that there are two elements, B and C, such that AB equals B, A equals the identity, and C also works for this. AC equals CA. Then we want to show that B equals C. This is our claim. So how can we prove this? Well, so what are we going to start by considering? If we have AB equals E, if we multiply by the left on both sides by C, because these are two-sided inverses, okay, this means that CAB equals C times E. All right, obviously E is the identity, so this is just C. But then by the associative property, CA times B equals, well, CA, this is supposed to be an inverse, so this should be equal to E times B. But E is the identity, so this should just be B. And that means that B is equal to C, which proves that these two inverses are the same. Okay, the inverse of an inverse is the element itself. Well, I mean, if A inverse times A equals A times A, pardon me, A inverse equals E, then A satisfies properties of the inverse of the A inverse element, and therefore is the unique element to do so by what we just deduced. Okay, how about AB inverse equals B inverse times A inverse? Well, if we have B inverse A inverse and AB, we can use the associative property to make this B inverse A inverse A B, which is B inverse EB, the identity. That's just B inverse times B. You can combine the identity with either one of them without changing it. And B inverse times B is just E. So this works as an inverse on the left, and will also work as an inverse on the right. AB, B inverse A inverse. Same deal, associative property. Do associative. So this is A, B, B inverse, A inverse. This is associative. This is going to be A, E, A inverse, which is just A inverse, which is just E. So that tells me that B inverse A inverse is my special inverse element for AB. Okay, and as we know, there's only one element that works that way, because the inverse is unique. Okay, One more result to show, and then we'll call it a day. If you have A, B, and C in a group, if you know AB equals AC, that means that B equals C. And the reason for this is quite simple. You can multiply on the left on both sides by A inverse without affecting equality. And this tells us that E times B equals E times C, which means that B equals C. And the same holds for BA equals CA. You can multiply on the right by A inverse. And that tells us that BE equals CE, which means B equals C. Okay? So whenever you see an equation like this, where you have the same group element on the same side, you can pull it off without affecting the truth of the equality. And this is a cancellation law. Okay, so that's it for the results I wanted to show today. Hopefully you got a flavor for the type of basic properties you can prove using the group axioms. And I will see you in the next class. Take care.